In our new unit, we will begin looking at polynomial functions, and specifically looking at higher degree polynomial functions. Believe it or not, we've been looking at polynomial functions since Math 1. The straight line is a polynomial function, x to the first power. And in Math 2, in the beginning of this Math 3 course, we spent some time looking at quadratics, x to the second power functions. And from here, we're going to start to look at what happens when we start to add degrees. And to begin thinking about polynomials, it's going to be helpful to understand their graphs. And for polynomials, understanding what's called end behavior is the first step. Now to refresh, polynomial functions have a form that follows the given form here. Y is equal to a x to the n plus b x to the n minus 1, so on and so forth. Now this could be slightly confusing notation, but the basics here is that you have a variable and the exponents are all whole numbers. So a couple of examples are given here with y equal to 2x squared minus 3x plus 7, a very standard quadratic polynomial. But not all of these require every exponent to count as a polynomial. Notice that these two skip over. Here y equals 1/2 x to the fifth, x to the fourth and x to the third are left out. It goes right to negative 3x squared plus x. That's okay. All of those exponents are whole numbers. Same with y equals 4x to the third minus 5. It does not matter that all of the values aren't there, just that we have whole number exponents. And so the graphical behavior, right, is going to depend on the turning points and zeros, which we will start to look at later on down the road, but more importantly here today we're going to look at end behavior. Right? So symbolically, what is the function value f doing as x approaches positive or negative infinity? So let's look at exercise number 1. Here y is equal to negative 1/2 x squared plus 3x plus 4. So go ahead and grab your graphing calculator and let's produce a sketch here. Open up your y equals, plug the function in. We are given a window size here, so let's plug all of those different pieces into our window. And let's get a graph of that function so that we can see what's going on. Now, of course, we see this as an x squared function. We know it's going to be a parabola. We see that a value is negative, and it's a little bit wider, maybe plump after the holidays. But what we want to start to think about is what's the end behavior for this function. As x is approaching positive infinity, or as x is going right, what is y doing? Well, here, y goes down. It's approaching negative infinity. As x is going left, or as x approaches negative infinity, again, y is also going down, or y approaches negative infinity. So the end behavior for this function is as x approaches negative infinity, y approaches negative infinity, and as x approaches infinity, y approaches negative infinity. The end behavior matches on both ends. And as we've already learned about quadratics, the end behavior is going to match. They're either both going to go up towards positive infinity or down towards negative infinity. But let's see what happens when we involve cubic functions. Cubic functions are x to the third functions. So here we have two different cubics that are graphed. Now how do these two cubics differ from quadratics? Well, the first thing that we notice is that the behavior at the ends is now mismatched. One is heading negative, the other positive. Why do you suppose that f of x is looking one way and g of x appears the opposite? Well, if we consider the leading coefficients, the leading coefficient for f of x is positive, whereas the leading coefficient for g of x is negative. This is causing our graphs to behave the way they behave. So here in the first example, as x approaches negative infinity, we can see that y also approaches negative infinity. And as x approaches positive infinity, so does y. And so for these cubic polynomials, whatever x does, y does when the leading coefficient is positive. But when the leading coefficient is negative, as x approaches negative infinity, y does the opposite. It heads to positive infinity. And as x heads to infinity, y heads to negative infinity. So odd degree polynomials seem to have end behavior that mismatches at the ends. But if the leading coefficient is positive, x and y approach the same, where if the leading coefficient is negative, the opposite occurs. So let's look at a quartic function. These are our fourth degree polynomials. Now you're already given the graph of f of x here. Let's describe the end behavior of this quartic function. As x heads towards infinity, y heads towards infinity. As x heads towards negative infinity, y still heads towards infinity. Does this end behavior more resemble a quadratic or more resemble a cubic? Well, of course, this more resembles a quadratic because the end behavior is matched. So in part C, grab out those graphing calculators again and let's sketch g of x and see how these compare. When we plug g of x into our graphing calculator, apply the window that we're given, here is the graph we get. Why is it that this quartic function is pointing in the opposite direction as the first one? Well, again, if we pay close attention, the leading coefficient for g of x is negative, whereas the leading coefficient for f of x was positive. So we ought to be able to draw some conclusions about the degree and the leading coefficient of these polynomials. When the degree of the polynomial is even, the end behavior is going to be the same, whereas when the degree of the polynomial is odd, the end behavior will be opposite. When the leading coefficient changes sign, the ends of the polynomial will change direction. So let's see if we can apply this in exercise 6. What is the degree here in 6a? Well, we can tell it's going to be even because the end behavior matches. But the leading coefficient must be negative because it's pointing down. As x approaches negative infinity, y approaches negative infinity. And as x approaches infinity, y approaches negative infinity. In part B, we can tell that because the end behavior is mismatched, that the degree is odd. But because x does what y does, the leading coefficient must be positive. As x approaches negative infinity, so does y. As x approaches positive infinity, so does y. Now, to further understand the graphs of polynomials, we need to consider something that's called multiplicity. The multiplicity of a root refers to the number of times its factor appears in a given polynomial. In an example, if the cubic function f of x is equal to x plus 3 times x minus 2 times x minus 4, each of those would have a single root at negative 3, at 2, or at 4. Whereas you could have a 6th degree polynomial g of x with the exact same roots, but a very different shape. Notice that x minus 2 occurs twice. It has a double root at 2, or what we would call a multiplicity of 2. And the factor of x minus 4, or the root of 4, would have a multiplicity of 3. And so single roots, double roots, triple roots, and so on have very different behavior at the x-axis. Let's consider these 4 polynomial functions. Let's look at a first. Notice we have y is equal to x plus 4 times x minus 3. Now here, we can see what the roots are, but each of them is simply a single multiplicity. And so we would say this graph simply passes through or crosses through the 0. The roots are simply x is equal to negative 4 and x is equal to 3. And by leaving those, it's implied that the multiplicity would be 1. Let's look at b, because now all of a sudden, negative 4 something happens. And if we notice, there's a double root at negative 4, it occurs twice, and a single root at 3. So at negative 4, with that multiplicity of 2, we would call that a touch or a bounce. The graph approaches, hits the x-axis, and then returns. It does not pass through. Almost like when a quadratic has a vertex on the x-axis. 3 simply passes through because its multiplicity is 1. In 1c, we can see that there's a straight cross through at negative 4 because the multiplicity is 1, and we have a touch or a bounce at 3. Notice again, the single root at negative 4, the double root at 3. Thus, the roots for this would be x equals negative 4 and x equals 3 with a multiplicity of 2. And lastly, we have a double root at both negative 4 and at 3. x would equal -4 with a multiplicity of 2, x would equal 3 with a multiplicity of 2, and both would have a touch or a bounce at their root. So although the roots are the same, the multiplicity, you can see, makes a big difference in the way that the function behaves. So let's find all the zeros and the multiplicity for this function. What degree would this polynomial be? The first thing to note is that unlike the functions we worked with on the first set of problems, these functions are given in factored form, rather than in the standard form we saw previously. To properly identify the degree of this function, we'll need to add together the multiplicities, since if we were to multiply this out, the highest degree term would equal the sum of the multiplicities. So here we have a single root at x equals 0. We have a double root at x equals -6, or x equals -6 with a multiplicity of 2, and x equals 5 with a multiplicity of 5. Now if we were to add all these multiplicities together, the 1, the 2, and the 5, we would find that we have an 8th degree polynomial. The nature of the roots will dictate the behavior of the graph near the x-axis. So we've seen what happens when you have a single root, and we've also seen what happens with the double root. Right? The double root will touch and bounce back, the single root will cross through. But higher odd degree groupings have a very unique behavior, and that's known as a flex. They still pass through, but there's a little bit of a flex there. So if we were given the graph of f of x and we're told that this is a quintic or a 5th degree polynomial, forgive the typo, determine the zeros and their multiplicities here. Well, if we know together that these roots will add up to 5, and we can already see that there is a touch or a bounce there at -3, that means that we have a multiplicity of 2. That means that at x equals 1, we must have a flex, or a multiplicity of 3. So any odd greater than 1 multiplicity will cause a flex action at the x-axis. So lastly, let's see if we can apply our multiplicity knowledge here and come up with a sketch for the graph of y is equal to x squared times x plus 2 times x minus 3 cubed. Well, first, what would the degree of this polynomial be, and what is its end behavior? Looking at this function, it is in factored form, so we need to add the multiplicities. 2 plus 1 plus 3, that gives us a 6th degree polynomial. And because it's even degree and the leading coefficient is positive, the end behavior would be up. As x approaches -infinity, y approaches infinity. As x approaches infinity, so does y. What are the roots and their multiplicities? And what does this mean for the behavior at each root? Well, we can see that we have a double root, or x equals 0, with a multiplicity of 2, so that would indicate a touch. X equals -2, with a multiplicity of 1, indicating a cross through, and x equals 3 with a multiplicity of 3, which means we would flex. So let's see how to sketch this. First, sketch in the end behavior. So just leave yourself some arrows indicating that because this was even positive, we're going to finish up in both directions. Next, sketch in the zeros. And if the y-intercept is different than a 0, let's add that too. Then, sketch in the multiplicities. Pass through at -2, a bounce or a touch at 0, and a flex at 3. And then lastly, connect the sketch. Notice that the precision here is limited. We would need calculus or technology to perfectly graph this. So the pieces that we're going to be paying attention to are the end behavior, the zeros, and the multiplicities. So takeaways from today's lesson is understanding how the degree and the leading coefficient speak to end behavior for polynomial functions, and how the multiplicity of each zero causes the graph to act at the x-axis. Using the notes from this lesson, complete the following pages, 5 through 8, for practice.